This is number 59. And the first theorem is called the angle bisector theorem. And this one says, if a point is on the bisector of an angle, if a point is on the bisector of an angle, so they're talking about an angle. So let's draw that. And then they're talking about the bisector of the angle. What does that do? Cuts the angle in half, right? And we're talking about the rotation. So it takes this rotation and cuts it in half. So now you've just got two smaller rotations that are equal. So there's the bisector of the angle. And then finally, they're talking about a point that's on the bisector of the angle. So just somewhere on this bisector, doesn't matter, any point. So there's a point that's on the bisector of the angle. So what happens is, then the point is equidistant What does equidistant mean? Yeah.
I mean, I don't know how to, it's like the same on both sides.
Same. Equal means same. Good. And distance means same. Or distance, sorry. So this is same distance. Equidistant, just fancy way of saying it's the same distance. So it's equidistant from the sides of the angle. So if a point is on the bisector of an angle, there it is, it's going to be the same distance from the sides of the angle. Now, how to draw the picture is a little bit tricky because if you're going to go from this point to the side of the angle, should you go this way? I mean, there's a lot of different routes you could take. Should you go that way or that way or that way? When we're talking about the distance from a point to a line, how do you get there? The shortest possible way is how you should get there. So going here would be too long, going this way would be too long, but the best way would be to go straight there and make a 90. I don't know that I actually did a 90 there, but there we go, that's a little better. So when we're talking about the distance from a point to the side of the angle, that's going to make a 90, because that's the shortest possible distance. So then if we're going to go from that point to this angle, or sorry, to this side of the angle, we'll go like that. And what the theorem is saying is that this distance is equal to this distance, is equidistant. So if A represents that distance and B represents that distance, then the A equals the B. So when you have any point, so could have picked that one instead, but we picked that one. When you have any point that's on the bisector of an angle, it's going to be the same distance to that side as it is to that side. That's what this theorem says. All right, then the other theorem today is called the right triangle altitude theorem. And it says the altitude to the hypotenuse of a right triangle. The altitude to the hypotenuse of a right triangle.
For the interruption, jazz band students, please go up to the band room for your field trip. Thank you.
So the altitude to the hypotenuse of a right triangle. I'm going to draw a right triangle so we can kind of see what's going on here. So here's the right triangle. It's got a right angle. That's what makes it a right triangle. What is this side called? Hypotenuse, yeah. So just as a reminder, that's H for hypotenuse. And then what are these sides called? Legs. And one of them is shorter. So to help with today's discussion, I'm going to call this the short leg, and I'm going to call this the long leg. So short leg, long leg. That's the first time I've ever called them short leg and long leg, but I guess it's possible they're equal, so that wouldn't make sense then. But in this case, this one's shorter than that one, so that's the short leg, that's the long leg, that's the hypotenuse. Okay, then it's talking about the altitude to the hypotenuse. The altitude is a fancy word for height. So they're drawing in the height of the triangle. So that's the altitude to the hypotenuse of the right triangle. So that divides the triangle into two smaller triangles. Which we can clearly all see, right? We just drew in an altitude. And now we've got two smaller triangles. One over here on the right and one over here on the left. So that's not earth-shattering at all so far. The altitude to the hypotenuse of a right triangle divides the triangle into two smaller triangles. And those, well, that are similar to each other. So what I'm saying is that this triangle here is a mini version of this triangle here. So this triangle is a mini version of the larger triangle. Now I can't really call this the short leg anymore. I mean, it's the short leg of the largest triangle, but then it's the hypotenuse of this triangle. So that's why I got rid of the labels. So the theorem is saying that this triangle is similar to that triangle. And it's also similar to the original triangle. So the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to each other. So this one is a mini version of that one, and also similar to the original. So this one is a mini version of the largest one. And just to nail that home, I'm going to put some letters down. So triangle ABD is similar to triangle BCD, which is also similar to triangle ACB. ABD is the medium-sized triangle, and BCD is the smallest triangle, and ACB is the largest triangle that encompasses all of them. And what this theorem is saying is they're all similar to each other. If you take this triangle, blow it up just a little bit, it's the medium-sized one. And then if you take that and enlarge it just a little bit, it's the largest triangle. So they're all scaled up or down versions of each other. All right, so that's it for the note card. Title of the paper today is Angle Bisector Theorem. And we're going to start with number 7. And the directions say solve for the variable. So in this case, we have to figure out what n equals. And they also say name the theorem that you're using. So does anybody know how to do any of that? How to set up the equation or what theorem this is? Yeah, Maddie?
The equation would be n plus 4 over n plus 6 over,
Yeah, you're good.
and then equals 4 over n plus 1.
Good. So this divided by this equals this divided by that. N plus 4 over n plus 6 equals 4 over n plus 1. So that's how you set it up. And we'll solve it in just a second. But now we need to write down what theorem it is. Is it one of today's theorems? It's not. Because today we just had an angle and a triangle. And this is 3 lines. So it's not one of today's theorems. So it must be last week, maybe. Yeah.
Would it be the corollary to side splitter?
Yeah, it's the corollary to the side splitter. So it's the one we did on Friday. So you could get out note card 58 and look at that one to know that this was corollary to side splitter. Okay, I'm probably going to have time to go back and solve that, but I don't want to spend time on the algebra right now because I'd like to focus on the geometry for a little bit longer. So just leave some space. I'll probably go back and do that after I do a couple more problems. Okay, so next we're going to look at number 8. So we have to solve for the variable again and say which theorem it is. So anybody that can help out with any of that? Yeah, Charlie?
Is this the angle bisector theorem?
Yep, this is today's angle bisector theorem. Awesome. So then how do you set that up? theorem says that, yeah, go ahead, Charlie.
Which is like a equals b, so n squared minus 5 equals 6n plus 2.
Yeah, this time it's just equal. It's not talking about fractions. Just this distance is equal to that distance because it's a point that's on the angle bisector. All right, now that's a little bit tricky to solve. Why is it tricky to solve?
Because one's n squared and the other's 6n.
Yeah, this one has n squared and this has n. When you have both of those in a problem, it just makes it a little bit tougher to figure out what n is. So you subtract 2. So that's n squared minus 7 equals 6n. And then you subtract 6n. So then you get 0 on this side, which is what we wanted. Anytime you have n squared and n in a problem, or x squared and x, whatever the letter is, you want to get 0 on one side. And that bothers people because when it's just the letter, you don't want to get 0 on one side. You want to get the letter by itself. Okay, then once you get it to this stage, you have two choices. You can do quadratic formula or factoring. On this one, factoring is a lot quicker, so I'm going to do that. So you put an n here and an n here, because n times n is n squared. And then we're looking for two numbers that multiply to be negative 7. Yeah. That's close, except that adds to be negative 7.
Oh,
You're thinking good, though. If you took negative 1 plus negative 6, that would be negative 7.
oh, it would be 7.
Yeah, but you don't have to, I don't want to put you on the spot. You don't have to come up with the right answer, but you were thinking good because it adds up to be negative 7. But we're looking for two numbers that multiply to be negative 7. Yeah.
1 and
So positive 1 times negative 7 is one option. What's the other option? Yeah, you could change it, make it negative 1 and positive 7. So these are the two options for multiplying to be negative 7. Okay, then another reason why Rachel was on the right track is we do want it to add to be negative 6. So that's why she was remembering the adding. So which one of these adds up to be negative 6? The top one, right? Because 1 plus negative 7 would end up being negative 6. So positive 1 and negative 7 is the pair of numbers we want for two reasons. First of all, it multiplies to be negative 7. That's what we keyed on. And then second of all, it added to be negative 6. All right, then you split that up. And you get two answers on this problem, negative 1 and 7. All right, the next one I'm going to skip to is number 21. All right, so here's the picture for 21. And there's three letters we have to figure out, X, Y, and Z. And then we have to say which theorem it is. So which theorem is it first? Right triangle altitude theorem, right? It's a little bit different picture than this one because it's turned. But we still have a right triangle and a height of it. So it's the right triangle altitude theorem. All right, so we have three triangles in the picture. We have the mini one. So I'm going to turn that one. We have the medium-sized one. And then we have the biggest one. And according to the theorem, these are all similar to each other. So if you enlarge the mini one just a little bit, you'll get the medium-sized one. And then if you enlarge the medium-sized one just a little bit, you'll get the biggest one. So they're all the same shape, just not the same size. Okay, so for the mini triangle, what is the hypotenuse? I'm not asking for the answer necessarily. I'm just asking for the number or the letter. Yeah.
30.
For the mini one.
Oh, for the mini. Oh, then 6. Sorry.
Close. Now you're at least looking at the at the correct triangle, but the hypotenuse on this one is not 6.
Oh, it's Z?
Yes. See how the Z is across from the 90?
I thought it was trying to be a number of the
It's all good. It's all good. Thank you for being willing to talk, because it gets boring if I'm the only one talking. So see how Z is the hypotenuse for the mini one? Okay, then what is the 6?
One of the legs.
It's one of the legs. Is it the short leg or the long leg?
Short leg.
It's the shorter leg, right? So that means it would go here. And we don't know what the longer leg is. It's Y. So on the mini triangle, there's only one thing we know. We only know the shortest side at 6. But we don't know the hypotenuse. We don't know the long leg. Okay, then on the medium-sized triangle. So just looking at that. What's the hypotenuse?
X.
Yeah, good. X. Awesome. No, you're fine. See how X is across from the 90 on the medium-sized triangle? And then the Y. Is that the short leg or the long leg? Short leg, so I'll put it here. And then this long leg here. How long is that? Yeah, 24, right? 30 minus 6. See where she got that? Okay, then for the largest triangle, the hypotenuse is 30. And the short leg is Z. And the long leg is X. Okay, again, according to the right triangle altitude theorem, all these triangles are similar to each other. So since they're similar, what can we do with the sides? What do we do with the sides? Yeah. Make the side fractions equal, right? That's how similar triangles work. So let's see, x over 30 equals 24 over x is one possibility. See that? So x over 30 equals 24 over x. And that's good because that's going to help us solve for x. So x times x is x squared. 30 times 24. $720, so x is the square root of 720. We haven't been simplifying radicals this year. I know you did that a little bit last year. We'll be doing more of that in the next week or so. But for now, it's okay. Just leave it as square root 720. Okay, so now we know what the x is. It's the square root of 720. Okay, what's another fraction we could set up?
Y over 6 and then 24 over Y.
Yeah, y over 6, 24 over y. Good. Everybody seeing that? That's going to help us because then we can solve for y. So So y times y is y squared, 25 times 6 is 144, so that one comes out to 12. We got 12 for y. Okay, last but not least, let's do z over 30 equals 6 over z. So z squared is 180, and z is the square root of 180. Okay, I said I was going to maybe not have time to go back and finish number 7. I don't really, but you don't have to finish number 7 either. So just, we wrote down the theorem, we wrote down the formula. So don't finish that. Let's go back and start on